So we'll get started. Lucas Aronson, can you introduce our first speaker here?
Yes, happy to do so. Yeah, good morning, everyone. My name is Lucas Aronson, and I'm a geotechnical engineer. I'm talking from the Vancouver office, which is on the unceded ancestral territory of the Musqueam, Squamish, and Tsleil-Waututh people. So it's really great and it's my pleasure to introduce the first speaker and opening this year's BGC's R&D Symposium. So Khatereh Roghangar is currently working actually as a BGC summer student, and she's working in the Calgary office. She's a third-year PhD student at the Department of Civil Engineering at the University of Calgary, and she works on her research work entitled Reliability Analysis of Railway Embankments Built on Permafrost Considering Climate Change. And that project is part of the Permafrost, NSERC Permafrost Net program. And she's working under supervision of Dr. Jocelyn Haley. BGC is an active partner in NSERC Permafrost Net, which is a conglomerate of 11 universities and industry, as well as government and Indigenous partners. And they all share the common goal of boosting Canada's ability to monitor, project, and adapt to large-scale permafrost thaw, as well as the related consequences. The network is led by Professor Stefan Gruber out from Carleton University. And BGC has a long relationship with Dr. Gruber and his research team in Ottawa out of Carleton University. The network's stated objectives are really to share and apply research findings by producing knowledge products and practices for all the different stakeholders. And I think the opening presentation by Khatereh just exactly fits that goal, and I'm looking forward to her opening this year's BGC's R&D Symposium. And with that, I'm passing over to Khatereh for her presentation.
Thank you, Lucas. Hi, everyone. My name is Khatereh Roghangar, and I am currently a PhD candidate in geotechnical engineering at the University of Calgary, and I am working under the supervision of Dr. Jocelyn Haley. Today, I am presenting my thesis, which is titled as the Reliability Analysis of Railway Embankments Built on Permafrost Considering Climate Change. So the topics of today's presentation are the permafrost concepts, for those of you who are not familiar with them, my research objective, the methodology that I'm using, the current progress, and the next steps in my thesis. So just a little bit of myself. I have a bachelor's degree in civil engineering, and I have a master's in geotechnical engineering, and I am a PhD candidate in geotechnical engineering as well. Okay, so permafrost refers to a thermal state of the ground, and we can define it as the ground that remains at or below 0 degrees centigrade for at least 2 consecutive years. As you can see here in Canada, we have 4 types of permafrost, which are continuous, discontinuous, sporadic, and isolated. And we've categorized these groups based on the percentage of the coverage in the land. And climate change is affecting many aspects of our lives, and permafrost is also one of them. And based on the worst case scenario, in the next 70 years, we're going to have 5 degrees centigrade of air temperature rise. And this air temperature rise, or as we can say, the climate warming, is causing many problems to the permafrost. Like we have this active layer in the permafrost regions that we can define it as the layer that freezes and thaws seasonally. And the warmer the climate, the thicker the active layer. And then we're going to have the warmer permafrost and the thawing permafrost. And this thawing permafrost is causing many problems like the thaw settlement, the thermal cracking, the frost heave, and etc. And because we have many infrastructures built on permafrost, we're gonna face with many issues in the infrastructures as well. But the focus of our study is the thaw settlement among all of the hazards that we may face in the future. So there should be some methods for design and adapt the permafrost embankment to climate change, one of which is this using the standards and guidelines. So one of them is the CSA Plus, which we can use it for designing and adapting the foundations in the permafrost, the TAG guideline, which we can use for the transportation, and we can use it for the roadways or railways, and the CNA B&Q, which we can use for the site investigation for building foundations in permafrost. But unfortunately, none of them has quantitative assessments for assessing the climate warming effects on the permafrost embankment. And the other method that we can use is using the risk maps, like this one that I've presented here. We can get the high, moderate, or low potential hazards, for example, for the settlement. But the problem with the risk maps are that they are based on the qualitative databases. And as you can see, the problem here is that we are missing some quantitative assessments for the climate warming effects. And that's why we've defined my research objective as assessing the impact of permafrost degradation due to climate warming on the performance of infrastructure embankment. First of all, I'm going to assess the impact of climate warming on the infrastructure. Then I'm going to do a reliability analysis of railway embankment, specifically in the infrastructures built on permafrost. And then I'm going to do a sensitivity analysis to find out the key parameters that are impacting the failure of the embankment, and the reliability analysis of Hudson Bay Railway as the last sub-objective. So because we are doing a reliability analysis, we've also defined our methodology based on the reliability analysis steps. First of all, we should define the system and the limited state function, which is our calculated thaw settlement and the actual thaw settlement. Then we should collect the data and calculate the probability of failure of the infrastructure, and we can conclude the results and the sensitivity analysis. So in the first step, we've done a thermal analysis using the TempW from the GeoStudio software. We've chosen 3 sites in different permafrost zones along the Hudson Bay Railway, which are on the continuous, sporadic discontinuous, and extensive discontinuous permafrost. And we've got their initial data like the temperature and borehole and water content and like site characteristics from the old reports of the ABA engineering consultants. And then because we wanted to have some general ideas about the future active layer thickness and settlement in these regions, we've categorized the soil columns or the simulations to sand, silty, silt, silty clay, and clay. And based on these graphs, you can say that, okay, in the next 40 years, how much of a settlement I'm going to have if I am in the extensive discontinuous permafrost and in like one of the RCP climate scenarios. And we've done this step for the 3 major RCP climate scenarios, the RCP 2.6, the 4.5, and the 8.5. In the next step, we have done a water content sensitivity analysis to figure out how much of water content, or in the permafrost, we can say ice content, changes the active layer thickness and settlement in different types of soil. As you can see here, for example, in continuous permafrost, the more the water content or moisture content, as we can say, we're going to face less settlement and less active layer thickness change. And that's reasonable because of the thawing permafrost is mostly related on the ice content of the permafrost. And the other result that we can conclude from these graphs is that the finer the soil, the more susceptibility of the soil we have toward the settlement. And we've kind of got the same results for the extensive discontinuous, but the major difference between the extensive discontinuous and continuous is that the differences in the settlement are more. So if we are also in the warmer climate, we have more susceptibility of the soil to the settlement and the active layer thickness. The sporadic discontinuous results were kind of different because in the sporadic we have like really warm climate. And the problem with that is, for example, if we have 20% of the water content, we will not have permafrost in the next 50 years. And that's why there are some missing points on this graph. The other factor that we've done the sensitivity analysis on was the depth of the model. And we've done it because we had this question that how much deep we should go into the ground for our simulation and we still get persistent results. We've done this analysis in two water contents, the 30 and the 90, because we wanted to see that is the depth of the model is a direct factor in the settlement results or is it indirect, and is it related to the water content or not. So as you can see here in continuous permafrost, we don't face that much of a change after 30-meter depths of the model. And we've kind of had the same results for this extensive discontinuous. So we've concluded that if we have low water content percentage, depth of the model is only critical when we have 0 to 30 depths of the model. And in the 90% water content, we've saw that we have more changes in the results rather than when we had the 30% water content. And we've seen the same results in the extensive discontinuous and also in the sporadic discontinuous. And we've concluded that depth of the model is an important factor, but it's not as important as the water content and it's totally related on the water content. But if we want to have persistent results, no matter of the water content, how much it is, we should have at least 40 meters of depth in the models of the simulations with TempW. In the next step, we've started to do a probabilistic analysis of our thermal analysis. We've done this step because we needed this for our reliability analysis. And unfortunately, because GeoStudio does not provide a probabilistic analysis for the thermal analysis, we wrote our own code in Python, and the code generates the random variable, for example, like the water content based on its normal distribution, changes the inputs in the GeoStudio, runs the simulation, and gives us our result. So when we've changed the water content based on its normal distribution, we got these results. And as you can see here, the settlement is much more variable than the active layer thickness. And we've kind of got the same results for the dry density, but the difference between the dry density and the water content was that the variabilities got closer together. But when we've varied the frozen heat capacity and also the unfrozen heat capacity, we got less variability in the settlement and in the active layer thickness. And less variability means more accurate results, and it means that the water content, no matter if we enter it deterministically or probabilistically, has the greatest impact on the settlement and the active layer thickness in the future. In the next step, we are going to develop some equations for the future toss settlement. Using this equation, you will be able to calculate the actual toss settlement based on the type of the soil and the permafrost regions without any simulations. And then we're going to do a Monte Carlo simulation on the thermal analysis to do the reliability analysis of railway embankment infrastructure. And the last step of our work is to do a reliability analysis of Hudson Bay Railway. And I should mention that we've installed some instruments in the Hudson Bay Railway this summer, and we're gonna get the results the next summer, and we're gonna do the reliability analysis based on the new data that we are gonna get, and we're gonna kind of validate the settlements and the results that we got in our thermal analysis based on the new data. And these are the references that I've used in these presentations. And thank you very much. I would be happy if you have any questions. And thanks.
Yeah, thank you very much, Khatereh, for opening today's seminar. So if there's questions, yes, please put them in the chat. Or you also got her and our email addresses. So I guess if there's some follow-up question, please, yeah, don't be shy and reach out.
Lucas, there is a question in the Q&A, Lucas. I'm not sure if you can see that. Yeah.
No,
we'll encourage people to use the Q&A if we can for the questions, and then the chat's also available.
Thanks, Lauren. Yeah, technology, that doesn't work without
Yeah.
Okay. Okay, I'll read it out. So, do you have any comment on widespread problem might be for Canadian Railway? So just like, I guess in general.
I think the most important problem is the thought settlement and the railway, like the road we're gonna get, like the operation of the railway, we're gonna face many problems because of the settlement that is not consistent along the railway. And we currently also have many sinkholes along the railway as you go along the Hudson Bay Railway. And the bigger problems might be like the water, that we are going to be in the ponding waters or the sinkholes, and the water will change the soil characteristics. And because we are not considering that, I think that might lead to even bigger problems that the thing that we are calculating right now.
Thanks. And maybe just to add to that in a more of a global context, Canada doesn't really have a lot of railway within permafrost environments. It's mostly the Hudson Bay Railway that is in permafrost. But if we're looking at other northern nations, they have significantly more railway in permafrost environments where definitely future changes have significant problems. Okay.